This is our fifth video on light waves, and in this video we will continue practicing questions that I haven't solved for you yet. So again, I think you know all the information you need to solve these questions. When you see a problem, I'm not going to pause it or remind you. Try to pause it yourself and solve the questions on your own before I solve it for you. So let's look at some questions. In this question, they say that in the figure provided, assume that the incident beam strikes the prism with an angle of 60 degrees. And if the top angle of the prism has a measure of 60 degrees, what are the angles of refraction of red light and violet light when the beam emerges from the other side? Use index of refraction for the red light 1.502 and for the violet light 1.53. So the incident angle is 60 degrees, and that is theta 1 in our picture, and I drew the red light and the blue light path. So the blue light will refract the most because it has the shorter wavelength and higher frequency, so it slows down the most in the other medium, when the red light slows down the least in the other medium. And so I'm going to use the Snell's law, where I have n1 sine theta 1, which is 60 degrees, is equal to n2 sine theta 2. And that is going to be the angle that I have, the refracted angle. So maybe I'll just have this line right here. So this is theta 2. And from here, I can find that the refracted angle, theta 2, is equal to arc sine, the inverse sine of n1 sine theta 1 divided by sine by n2. So theta 2, not q2. So theta 2, if I plug in all my numbers, is going to be equal to 35.21 degrees. So what I have here is, this is 60 degrees, this one is 35.21 degrees, and so if this is the continuation of the prism, I'm gonna have another normal over here. And so when the red light arrives to that normal, I can calculate the angles here. So this angle right here, this whole thing, is 90 degrees. So if this part where red is 35.2 degrees, then the one that I have on the top is 54.79. So this is 54.79. The top angle is 60 degrees, this one is 60 degrees, and this one is 60 degrees, so it's the right prism. That means the angle that is left over here is 65.21 degrees. So this is 65.21 degrees. And because this whole thing is 90, then I know at which angle the red light strikes the normal. So that is the incident light for the second side of the prism. And that angle is going to be 90 minus 65.21, which gives me 24.79 degrees. So this angle right there is 24.79 degrees. So I can do the same Snell's law for the rest of the problem. So I'm going to do n2 sine theta, let's plug in the numbers now so it's easier. So I have 24.79 degrees is equal to n3 is the same as n1, so that is 1. And n2, we're given the index of refraction for the red light is 1.504, so I can plug in 1.502, so times sine of 24, and then I have sine of theta 3. So that is the angle at which the red light is leaving after it was refracted back to the outside, to the air. So I'm looking, this is theta 3. So if I plug in all these numbers, I will find that theta 3, so theta 3 is equal to 39 degrees. So I found at which angle it leaves, so I found the red light is leaving right here after it passes through the prism and goes back to the air, and the angle at which it's leaving with the normal to the surface of the prism is 39 degrees. So I get for theta 2 is equal to 34.5 degrees. I will use the same trick for finding the incident angle for the second one. So if these are the normals, and I know that it's gonna go something like this, and I found that this angle is 34.5, but this whole thing is 90 and this one is 60, then I can find what this angle is equal to. So 90 minus 34.5 will be equal to 55.5. So this angle right here is 55.5 degrees. And this makes this angle right here 64.5 degrees. So what's left for the incident angle at which it hits the other side is 90 minus 64.5, which is 25.5 degrees. I'm gonna use it right now for calculating the angle 3. So I have n2 sine 25.5, because n2 is where the light is now in the prism, and is equals to n3, which is 1, and sine theta 3 is the one that I'm looking for, the angle at which blue light is coming out. So n2 is 153 for the blue light. Then I have sine of 25.5. And if I take arc sine of it, I'm gonna find theta 3. So this is arc sine of this whole thing will give me angle 3. And if I do all my calculations through the calculator, I will get 41.25 degrees is the angle at which the blue light is coming through, or coming out of the prism. In this question, they say a beam of light wavelength 615 nanometers in water, and the index of refraction of water and air is 1.33, is incident on the side of a tank, the sides of each of which are made of flint glass, and index of refraction is 1.66. The angle of incidence is 41 degrees. Find the speed of light in the glass. Find the angle of refraction with the glass, the wavelength of the light in the glass, and the critical angle for the glass. And the picture wasn't related to the question, so I just took it away. So let's look at what is given. I'm gonna write all the information that is given before I start solving the problem in the graph and the picture. So here is the information that is given. I have the index of refraction in the water, and I have index of refraction in the glass, and I have the wavelength in the water, 615. So they asked me to find the speed of light in glass. So the speed of light in glass is equal to n glass is the speed of light in the vacuum over the speed of light in the glass. So that gives me the speed of light in the glass is equal to c over the index of refraction of glass. I have 310 to the 8 divided by 166, and I will get 1.81 10 to the 8 meters per second. So that answers A for B, they ask me to find angle of refraction with the glass. So I have index of refraction 1, which is the water, sine of theta in the water, the incident with the water, equals to n of the glass, and sine of theta in the coming out of the glass. So I believe it's this angle is 41 degrees from the water, and this one is the one that they are asking you to find. So this is not the 41. So this is the angle that, not this one, but this angle is the one that they ask you to find. So I'm gonna call it theta of the glass. So index of refraction in the glass. So I have index of refraction in the water is 133. Sine of the incident angle is 41, equals to index of refraction for the glass 66, and sine of theta of the glass. So theta of the glass is equal to arc sine, the inverse sine of 133 sine 41 divided by 166, and that will give me 31.8 degrees. So I have this part. For C, let's scroll a little bit lower, and for C they say the wavelength of the light in the glass. So I know that for C I'm gonna do a little trick. So I have n of the glass is equal to c over the velocity of the glass, and n of water is equal to c velocity of water. Then I have c is equal to velocity of glass, n of glass. And so if I solve each of these equations for C, I can also say C is equal to n of water, velocity of water. So from here, if I replace velocity with frequency times the wavelength, I will get n glass, frequency, the wavelength in glass is equal to n water, frequency, wavelength in water. Then I can cancel the frequency because frequency doesn't change. Then I just derive the formula. N glass, lambda glass is equal to n water, wavelength in water. So n glass is 166, and they ask you to find the wavelength in glass. So that is wavelength in glass. And water is 133, and the wavelength in water is given 615 nanometers. So from here, I can calculate the wavelength of glass is equal to 615 10 to the negative 9 nanometers times 1.33 divided by 1.66, and this will give me 492.7 nanometers. So that would be the wavelength in the glass. And the last part they ask you to find is the critical angle for the glass. So critical angle is only possible when the angle is incidence, where the angle of refraction is 90 degrees or greater, and the light must be traveling from an optically more dense medium to an optically less dense medium. That means if I have a light that is coming from the air to the glass and then into the water, the critical angle, so if the motion of the light is in this direction, then the critical angle is going to happen between the glass and the water. So this will be my critical angle, and I'm going to call it theta 1. And my critical angle only happens when the angle of refraction is 90 or greater. so all the light will be reflected back. So this angle is 90. So this is my N1 and this is N2. So I have this is D. I have N1 sine theta 1, the critical angle, is equal to N2 sine theta 2. So for N1, I have the glass, which is 166. This is the angle I'm looking for, the critical angle, and equals to water is 133, and sine of 90 degrees is 1. So the critical angle for glass water would be arc sine of 1.33 divided by 1.66, and that is equal to 53.2 degrees. So previous question was very interesting. It had a lot of little details and I like that question. So we want to solve as many complicated questions as we can because we're learning more and we're understanding the concept more. So every time we solve the question, we not only learn how to solve the question and use the method we know, but we also we learn different concepts about the problem. So in this question, they say a double slit experiment, the slits are separated by 0.1 millimeter. The slits are illuminated by 585 nanometer light. The screen is 4 meters from the slits. Find the difference in path lengths for waves coming through the slits for a second order bright fringe. So I drew for you a picture, the one that I used when I was teaching you the double slit experiment formula. And I have two triangles. One is the green triangle, and so this will be my green triangle. And from the green triangle, I have the tangent of theta is equal to y2, this is the length to the second fringe, divided by L. And for the orange triangle, I have sine theta, and remember the sine and tangent of theta is equal to each other, or equal to each other when the angle is very small, and that is equal to the opposite, which is delta, which is equal to m lambda, divided by the distance between the two fringes. So I have the fringes right here, and the distance between them is d. So that's the distance between here and here, between the openings. So that is divided by the distance. So if we did have the information about what the second fringe, how far it would be, we would be able to solve by setting these two equations equal to each other, but it's not given. But what they did give me is the wavelength. So because I know the wavelength, I can actually use this formula to calculate how far they are apart. So I could use that delta is equal to m lambda, and that tells me by how much the longer wave is longer to cause the constructive interference at the second place, at the second fringe. So this delta is equal to 2 because it's the second one. So there's 2 wavelengths difference between those two red rays or lights, and the wavelength is given 585 nano. So the delta is equal to 1170 nanometers. In this question, they say the distance between two slits is 0.05 nanometers and the distance to the screen is 2.5 meters. Find the spacing between the first order and the second order bright fringes for yellow light with a wavelength of 580 nanometers wavelength and the frequency of the light. So I can use again the double slit experiment formula, double slit formula. So I have y is divided by L, the distance to the screen, in m lambda divided by the distance between the fringes. So from here I can find that y to the first fringe is equal to L times m lambda divided by d. So if I plug in the numbers here, I have L is 2.5. It's the first fringe, and the wavelength is 580 nanometers, so 10 to the negative 9. And then the distance between them is 0.05 10 to the negative 3. So y1 is going to be equal to 0.029 meters. For the frequency, if I need to find the frequency is equal to the speed of light, or speed divided by the wavelength, velocity by the wavelength. So I have 310 to the 8 divided by the wavelength is given 580 nanometers, 10 to the negative 9, and that will give me 517 10 to the 12 hertz. In the next question, they say a thin layer of oil and the index of refraction is given 128, splits into the surface of nearby lake. It produces maximum reflection or for orange light 600 nanometers wavelength. Assuming the maximum occurs in the first order, determine the thickness of the lake. So for the case that we have here, it is N1 is less than N2 and less than N3. And because we have air, oil, and water. And for constructive interference, we would have 2 times the distance the light travels through the oil, and equals to m lambda n in that medium, which means it's 2 times the distance the light travels. It is m, and for lambda n, I would have to do lambda in the vacuum divided by n, the index of refraction in the oil. So if I'm looking for the distance that is equal to m is the first bright fringe, or the first circle, the Newton circle, and that is, the wavelength is given 600 nanometers, negative 9, and divided by the index of refraction between the oil and the air is 1.28, and times 2. So the distance is going to be equal to 234.4 nanometers. In this question, they say a beam of light is emitted in a pool of water from a depth of, called it H, 67.5 centimeters. How far away relative to the spot directly above it, the length is x in the diagram, must it strike the air-water interface in order that the light does not exit the water? So that means critical angle that I have to find. If I find this critical angle, that angle is exactly the same as this angle. So these two angles are equal to each other. So I'm gonna use the Snell's law. So this is my N1 and this is my N2. My angle 2 is 90 degrees, the critical angle, and the incident angle is theta 1. So I have N1 sine theta 1 is equal to N2 sine theta 2, which is 90 degrees. N1 is water, which is 1.33, I'm looking for the critical angle theta 1, and M2 is air, which is 1, and 90 degrees sine is also 1. So theta for the critical angle would be equal to arc sine of 1 over 1.33. So that will give me that critical angle. I get 48.8 degrees. So this is my critical angle. And now I can look at this red triangle. And from this red triangle, I know the height, the depth of it, h, 67.5 centimeters. So I can use tangent of this critical angle is equal to x over h. Then from here I can find the distance at which it should strike. So that gives me x is equal to h tangent theta 1. So x is equal to h is 0.675. I convert centimeters into meters. And then I have tangent of 48.8 degrees. So x is equal to 77.1 centimeters, or 10 to the negative second meters. This will conclude our fifth and probably last video on light waves. We saw very many different questions related to double slit experiment, thin film, index of refraction, and Snell's law, the apparent depth questions. So this was all related to the light waves, and the next set of videos is going to be on geometric optics. And in geometric optics, we're going to look at the mirrors and the lenses. And we're going to still use some of the knowledge we learned about the light in these videos in the next one. And I'll say thank you for watching this video, and I'll see you in the next set of videos or other videos that I record. Thank you.